Hello, this is Matteo Torrejon, and welcome to Lab 3 Circuits. Introduction and purpose. In our experiment, we needed to prepare a circuit. We did this to observe the behavior of the circuit as it was built out of ammeters, light bulbs, voltmeters, and resistors. By observing its behavior, we could determine with Kirchhoff's rules, including the node and loop rule, to predict the behavior of the circuits we created. And our results were that we were able to effectively utilize Kirchhoff's rules to learn how a circuit behaved with some hands-on experience, from building it to using it, and measuring the voltage running through it. And so for our main physics ideas, first we have the node rule, and the node rule explains how a circuit behaves and how when the current flows into the node, it must be equal to the current flowing out of the node. This also aligns with the conservation principle, which is consistent in many aspects of this physics class. And second is the loop rule, which explains how all the potential differences that run through and around a circuit loop have to sum up to zero. This is also explained with the path of independence, which occurs in circuits, and the conservation of energy in it as well. Finally, we have Ohm's law, in which Ohm's law shows the relationships between the current, voltage, and resistance in a circuit. Ohm's law says that current is directly proportional to voltage and indirectly proportional to resistance. Predicting the currents that are in the two ammeters. From the principle we explained, we should see that the current is expected to be the same as each of the ammeters. So this is explained by the node rule because the current that enters the first ammeter has to be equal to the current that exits from the second, where the total R was 47 plus 100 is equal to 147, the total V equals 1.5 plus 1.5 is equal to 3, V equals IR, where R is equal to I times 147, where I is equal to 0.02 A. So the measurements that we got on the ammeters were around 21.1 milliamps and 18.6 milliamps, and then these were close to the 20 milliamps that we were supposed to get. What would happen to the two readings if the connection of one of the ammeters was switched? Once the connection of one of the ammeters was switched, then the magnitude would be the same, but the sign would change. So, for example, our first ammeter would now have a reading of negative 21.1 milliamps. What would happen to the reading if there was a switch between the ammeter and the voltmeter? Well, the voltmeter would actually read the 3 volts since there is not a change in the voltage between the EMF and the voltmeter. However, the ammeter would read 0 or near 0 volts because of the high resistance nature of the voltmeter. And lastly, the current would actually not be able to reach the second ammeter because it would be suppressed by the resistance of the voltmeter, which has that high resistance nature. Measuring the potential differences in the circuit. So these are the voltage measurements that we received in our experiment. From what we can see in our first point A had 3 volts as the EMF source. We had two 1.5 volt batteries together. Furthermore, the ammeter measurements are also interesting because they have the similar current magnitudes at each of the locations. However, although the sum should actually be 0, even though it's not because of the full loop around the circuit as energy is conserved. So here we can see some of our results where we have a voltage difference graph. This is our voltage difference graph that we got, and this is the graph of the voltage differences plotted across different points in the circuit. And so after adding up the differences, the sum turned out to be 0.6 volts, which is likely due to errors during the experiment, as we were supposed to actually see 0 volts to be our sum. And so results, what is the resistance of each circuit element, where R is equal to V over I? R at 47 is equal to 1.03 over 0.02, which we got 51.5 ohms. R at 100, we got 110 ohms. R at the wire, we got 0 ohms. And R at the ammeter, we also got 0 ohms. Connect the voltmeter across the 100 ohm resistor again and note the ammeter reading. So the ammeter reading after making the change was 19.5 milliamps across the circuit, which was actually a good expected value since it was near the 20 milliamps from before. And the reason why it's not higher is because of the high resistance that the voltmeter has, and it actually has little current running through it, which is why the ammeter has the close reading of 19.5 milliamps. And so for RC circuit, while the capacitor was charging, the 10 and 20 ohm resistance light bulb actually dimmed over time. The reason why this occurs is because the positive charges on the positive plate start to resist the flow of the electron because the repulsive force becomes stronger. Then, when we directly connected the capacitor to the light bulb, we experienced the same phenomenon. The light slowly started to dim because there was no EMF that was keeping the voltage difference across the circuit, where our 10 ohm bulb lasted 24 seconds and our 20 ohm bulb lasted 1 minute and 36 seconds. And so for a what if, so a capacitor could charge in an instant if there was no resistance in the circuit, or if the resistance in the wire that carries the electrons in the circuit, if there was no resistance. However, in the real world, EMF sources and wires have non-zero resistance, which is why you can never charge a capacitor in an instant. That's why it took our resistor around 50 seconds to fully charge. And so for our errors, there were likely errors with our voltmeters. Our some groups had defective equipment, and there could have been errors from interference from our surroundings. Thank you.